Well, this is the fourth presentation on RXs with nucleophiles. On the right here, under reactions, I've just listed the three that we have to consider if we have an alkyl halide. We have said that if the nucleophile is a strong base, you're typically looking at SN2 versus E2. And as we move down in basicity from weak base to non-base, we started to head towards SN1 E1 reactions. Weak bases can still do SN2, but it had to be, I guess, a primary or secondary alkyl halide for that to occur. We could not do SN2 chemistry with tertiary alkyl halides. So this order, SN2, E2, SN1, E1, can really maybe be thought of in this way: from strong base to weak base, and from primary alkyl halides, at least for SN2 and SN1, primary alkyl halides to tertiary alkyl halides. Tertiary alkyl halides are best for SN1, E1. Well, that's what we have here. If we circle the carbon-chlorine bond or carbon-bromine bond here, we have a tertiary RX. And SN1 E1 reactions are really what we're limited to as far as substitution chemistry. We can still do E2 with tertiaries, with strong bases. We can still do E2. But in terms of SN2, you cannot do SN2 with tertiary RXs. Now we have here water. It is both our non-basic nucleophile, but it's also our solvent. So we can have what's called in reaction savolysis, where the solvent reacts with the alkyl halide. That's often the case when you have water or ethanol as a non-base, but also as the solvent for the reaction. So we've tagged our nucleophile and we've tagged our alkyl halide, and according to the rubric, we would have an SN1 E1 condition. Product solvent, non-base, tertiary RX, SN1 E1. What's the first thing you should draw when you put your note down that you're going in this direction, SN1 E1? You should go to carbocation. Everything runs through the carbocation. That's why these two are often competing, is because they share the same rate-limiting step, the formation of this common high-energy intermediate called the carbocation. Just remember to draw it every time you write down SN1 E1 conditions for whatever reaction you're considering. Go to the carbocation. So we've done that here, and it's again for either SN1 or E1 we have to go to this carbocation. And from that we can then consider the attack on the carbon by the water and the loss subsequently of the proton, leaving OH behind, and the H from water going with the leaving group to make HBr as our product, or water coming in as a base towards one of these beta protons. We're still at this stage. Well, when you say, well, where are those beta protons? They're still there. We're just now considering the ripping off of those protons, not from this structure, but from this structure. And what's the difference? Well, maybe if you remember from way back, this carbon just got jacked up. It's hurting. It's full positive, so it becomes more electron withdrawing, making these protons fairly acidic. These weren't so acidic. These needed a strong base, for the most part, to rip them off. These don't. Very different in terms of acidity. This alkyl halide with the bromine still on, the alkyl halide without the bromine, we have a carbocation. These are very reactive in terms of attack directly on the carbon in a substitution manner, or on these beta protons in an elimination manner, where one of these is taken and we get our elimination product, the alkene, plus water. We give that proton back to the leaving group that we tore off with water, and we have HBr. something just to be quickly said about the two different types of reactions. SN1, we get 2 products. E1, you get 3 products. So at high temperature, elimination becomes favored because entropy favors at high temperature the production of more stuff than less stuff. At high temperature, E1 becomes favored. Some other notes. SN1, E1 reactions, believe it or not, are faster than SN2, E2 reactions. We can maybe tie this to the fact that once we go to carbocation, we have a very, very reactive species that can be approached from 2 sides in terms of how we attack the carbon and has very acidic protons. So yes, it's a rate limiting step to make this, and we have a small amount of this, but once formed, it reacts very quickly. That's not like SN2 and E2. Where SN2, we had to have some stereochemical restrictions. We had to come in 180 to the leaving group, 180 in degrees. With the nucleophile, had to come in a 180 degree towards the leaving halogen. E2, we had the restriction of antiparaplanar orientation of the leaving group to the proton that we're ripping off. Now, certainly of these two, E2 would be a faster reaction than SN2. But in general, SN1 and E1 together are generally faster than SN2 and, depending upon conditions, even E2 reactions. So SN1 is certainly faster than SN2. SN1 E1 is generally is faster as a reaction than SN2 and E2. SN1 products are favored with polarizable anions. What does that mean? Those polarizable anions were those large anions like chloride and bromide and iodide and sulfide. And at lower temperatures, we favor, again, at lower temperatures, over E1, we favor SN1 conditions. These are not very basic anions. E1 reactions are favored at high temperatures and with weak non-polarizable bases, such as your triethylamine. We might have with those, with triethylamine, its reactivity is not due to its polarizability but due to its basicity. Though it's weak, it's still more basic than it is polarizable, not a large atom as the nucleophilic site that goes and attacks. SN1 E1 reactions often result in greater number of both stereo and regioisomers. Basically, we lose control. When we have a carbocation that has to be formed as part of SN1 E1 reactions, we're going to find out from this, I guess from the second slide coming up, we're going to be talking about the carbocation the whole time here. And the problem is these carbocations, we lose control of both how we come at this carbon, from which side we can come in on this empty p orbital that we're looking straight down, from one side or the other. We're going to lose some stereochemical control. We're also going to see that the positive charge, depending upon these groups, can start moving. That causes loss of regiochemical control. We start to have regioisomers, where things are bonded, change, and how things are bonded to this carbon that has the positive charge start to change. So SN1 E1 reactions don't occur in strong base conditions. What would we have if we had tertiary RX in strong base conditions? I hope you're saying E2. Strong base conditions, and these tertiary alkyl halides would give us E2 conditions. Now, from here on out, we're just going to start talking about the carbocation, because this is the key. That carbocation formed, again, SN1 means substitution by nucleophile in a rate limiting step where the alkyl halide by itself, a unimolecular step by itself, without anybody else having to come in and make a particular contact with this. We just need some energy added to the system, some stabilization of the carbocation that will allow for this unimolecular step. But by itself, dependent upon no other concentration, no other compound, just some energy, this alkyl halide that's tertiary is going to fall apart to make our carbocation. plus the chloride as a leaving group. This is the key. This controls everything in terms of SN1E1 reactions. If we can make this lower in energy, SN1E1 reactions happen faster. So we have our SN1E1 reactions. What do we need to do when we write that down? Go to carbocation. Make sure you draw it, because you have to consider that as your rate limiting step. Once we form it, we can now consider the E1 reaction, where this water is a non-base, but it's going to act as a base because this is much more acidic. It's not like he's a strong base, but this is very reactive, not only at the carbon but at these CH3 groups, all 9 of them. Any one of those 9 protons can be abstracted by water to give us our final alkene. So I'm going to go ahead and draw that for just one of these carbons, the mechanism, but we could have done this with any of the CH bonds. We're going to draw that out. We can attack. This is just part of the second step of an E1, not the rate limiting step, but for the second step wherein we're going to E1 product. We attack the beta proton. The electrons in the sigma bond come down to a pi bond, and then we have our new pi bond. We have our acid proton that we've picked up with the oxygens, lone pair, one of those. And we've made, again, our final product, our alkene. Some things to say about this. We do not need to worry about antiparaplanar restriction here. So we can have a very fast reaction once we get to this point. Any one of those nine protons could have been abstracted in this way that we're showing. Any one of them can give us this one product. This is a non-polar product, so if we heat things up, not only do we make 3 things, the leaving group was initially kicked off, we make the acid and we make the alkene, so we get 3 from 2. 3, 1, 2, and 3 from 2 reagents. But at high temperature, if this starts to boil away from the solution, by Le Chatelier's principle, we can continue to drive more and more E1 reaction. Again, non-basic, non-polarizable nucleophiles result in a mix of E1, SN1 product. If we don't have polarizable anion or something with polarizability, we tend to just get a mix of SN1, E1 unless we go to higher temperatures. That favors E1. So if it's just water or ethanol, you can have the E1 reaction and the SN1 reaction. We can really only favor in this, we can only favor in this case the alkene if we raise the temperature. If we have non-polarizable nucleophiles that we're using for SN1, E1 reactions. If we were to again use thiols or RSH, this tends to favor more SN1 product because the nucleophile we're using is a large sulfur having polarizability. Anything in the third row or below elements have polarizability. I'm going to move a little more quickly here. We've said the carbocation is key. We need to worry about forming it once we know we have SN1, E1 conditions, so I'm just rewriting what we already have. This is a tertiary RX. This is a non-base. We may want to put now a note of it that it's just not polarizable or not large. Why? Because we have then an idea that both SN1, E1 reactions are SN1, E1 products are formed unless it's stating something about a very high temperature. So now let's go ahead and show the SN1 product. We've seen the E1 product. We attack not the protons, that was on the last slide, E1 product forming, but we now have just a direct attack on the carbon where we make from either side, we can make our oxonium ion, and we have loss of the proton to give us our neutral product, our SN1 product, which is right here, this alcohol, which would not be boiling out of solution at high temperature. That was our E1. So again, at just standard temperatures for these non-basic, non-polarizable nucleophiles, we're going to just have a mixture of SN1 and E1. Now, one thing to remember about the SN1 reactions is that solvent and substrate are very important, because as we go to a carbocation, so we can imagine this having formed with the leaving group having already left. This is called a benzyl carbocation, where we can stabilize this carbocation that is secondary CC, this carbocation, can be stabilized by resonance, and even better, not just carbons satisfying with their pi electrons, we can have a nitrogen that is going to neighbor a positive charge here. If we draw just the resonance form shown with this arrow, positive here, we can bring this down and have everyone with 8 electrons, as second row elements go, 8 valence electrons. The positive on the nitrogen now, and a more stable resonance form. Between these two, we know this is more stable, so this is contributing. They're all majors. There are some that we haven't drawn, but this would be the most favored major resonance form, where the positive charge is on the nitrogen. We would still make an attack here as the nucleophile reacts with either a weak base or non-base, reacts with this carbocation. We'll still attack here, but what we're saying is that with these secondary carbocations that are next to double bonds or next to lone pairs, they have some stabilizing effect. They're lower energy, so they're easier to form. So if we can stabilize the carbocation, you can increase the rate of reaction. You're stabilizing nearby transition states, you're increasing the rate of reaction. What's best to stabilize these carbocations? Well, solvent. You want a protic solvent, water, ethanol. These are great solvents for carbocations that have high dielectric constants. You want the substrate, that is what's around the carbocation, to help. More delocalization by resonance is huge. This helps a lot. This secondary reacts like a tertiary in terms of its speed and ease at which it can go to carbocation. It's like a tertiary. What do I mean by that? Electronically, it means that this is just as easy to form as a tertiary carbocation. We can also consider inductive effects. Tertiary carbocations have 3 alkyl groups around it. Secondaries have only 2 alkyl groups around it. And of course, the more alkyl groups you have, the more stable the positive charge is inductively. So stabilization of this carbocation is key. Resonance makes primary alkyl halides like secondaries and secondaries like tertiaries. This is in regards to electronics, not sterics. I'm not saying they are hard to get at the positive charge like a tertiary. No, I'm not talking about that. I'm talking about the electronics of this primary is like that of a secondary. The stability of the positive charge is like that of a secondary carbocation. So this primary is next to a double bond. That double bond can move over, and we have now 2 resonance forms that stabilize the primary carbocation. This is like a secondary CC in terms of stability. This primary is also like a secondary. Now, which of these two would be more stable? The allylic carbocation, that is a positive charge next to a double bond. They call that an allylic or allyl carbocation. Or is the benzylic or benzyl carbocation more stable? Hope you're saying the benzylic, because we certainly see more resonance forms, and the more resonance you have, the lower energy that positive charge is. So everything we can do to drive down this carbocation's energy, whether it be solvent effect, whether it be resonance, whether it be increased inductive effects, we're stabilizing the positive charge. The more stable, the more delocalized the positive charge, the faster the SN1 E1 reaction. This just sort of up here summarizes the inductive effect. We start off with just a CH3 plus having just hydrogens around it. These cannot give inductively through the sigma bonding, as well as 3 alkyl groups. Again, what we're looking at is a positive charge. You're looking right down the axis of a p orbital, and these methyl groups can inductively donate to the carbon through the sigma bonds. Now there's one other way these methyl groups can get electron density to that empty p orbital. They can do that through what's called hyperconjugation. That is, neighboring CH or CC bonds to this empty p orbital, neighboring CH or even CC bonds can line up in the same plane. Like in the plane of the paper here, I've drawn my empty p orbital, and we can have this CH bond straight up or straight down giving electron density through an overlap, not of 2 p orbitals, but of a p orbital and a neighboring sigma bond. So they call that not conjugation, but call it hyperconjugation. A little bit off from the energy, the stabilization you get with 2 p orbitals next to each other, one empty and one filled. This is a little different. So they call it higher energy conjugation. So we can get that overlap. Neighboring CH or CC sigma bond with an empty p orbital. And I've shown that down here. So we get inductive effects through the sigma bonding. Carbons are better at giving electron density to the carbon that has a positive because these electrons are at a larger valence shell. Hydrogens are harder. They're more dense. But carbon here can give more through the sigma bonding than hydrogen. We can also, again, have hyperconjugation along with sigma inductive effects. We can have hyperconjugation giving electron density to the empty p orbital. All that said, we get a more stable positive charge. Now what can happen, and this is what we'll close with, is if we have a positive charge on a carbon that is an empty p orbital and a neighboring CH bond, it can have this lining up, this hyperconjugation. But if it turns out that not only do we get a lowering of the energy, but we get this attraction of, through the hyperconjugation, this hydrogen can actually slide over to the positive charge if on the end of that slide or the end of that move, the positive charge becomes more stable. I think we see that here. Now we can't form primaries, but if we did, you'd have a quick lining up of a hybrid, or lining up of the sigma electrons with the p orbital, and it would slide over. So this would slide over to this carbon and leave the positive charge here. This would be secondary, where it started off primary. Now this is more common. You would see some alkyl group have a secondary to a tertiary. Secondary to a tertiary. So it's most often seen not with primary to secondaries, but secondaries to tertiaries. So watch out for secondary carbocations. They're really susceptible to hydride shifts or a neighboring CC bond. We would call that an alkyl shift or a methyl shift in particular. CC bonds, if that carbon is next to a secondary carbocation and we have a quaternary carbocation here, this can shift and we go from here at primary to a tertiary carbocation. That would be very favorable. Again, all these shifts, hydride or alkyl shifts, occur after we've established hyperconjugation. Line up, slide. Line up, slide. And that's it for this recording. We're done with now our 4 on alkyl halides. We had an introduction, just the roadmap. We had SN2. We looked at E2 reactions that compete with SN2, and now we've looked at SN1, E1 reactions. Bye-bye.